All right, so my name is Ben Consalvo. I work at Intel, an AI software engineering manager, and my background is in geophysics, and then started applying AI to my geophysics work, and then ended up kind of fully in AI. So the presentation I have today for you is seismic data to subsurface models with OpenFWI. All right, so first, maybe you here don't need as much background in this. Some of you might already be familiar with imaging and geophysics, but why care about seismic imaging and full waveform inversion? So seismic imaging helps us to explore the subsurface and unlock subsurface minerals that are essential to human thriving. And so on the top left, I'm showing an example of some seismic imaging from the Alaskan North Slope that I worked on during my master's degree. And then below that is a 3D image of a potential migration path for oil. And on the right-hand side, I have another application of imaging of full waveform inversion, which is in medical imaging. So there was a journal article published in Nature that outlined how FWI can help to find hemorrhages in the brain, and they use this cool brain helmet with sound sources and receivers, just like you would in the subsurface, and they're actually able to image the human brain similar to an MRI, but with sound waves. So you might ask, well, why not just use an MRI? Well, as you probably know, MRIs are expensive, and if you have metal in your body, you can't use them, and sometimes difficult to get an appointment for an MRI. But with this method of sound wave imaging, you don't need to. You can do the imaging without, even if you do have metal in your body. All right, so I just wanted to show you a few pictures of my time in the field for collecting seismic data, just some of my background. And so I've circled myself in blue. This is during my master's degree. We went out to the field, collected seismic data, just some of the background that I have in geophysics. Like I said, I started in geophysics and then moved into applying deep learning to my work. And so now at Intel, I help other AI developers to discover how they can use Intel AI software and hardware. So the real world problem that I wanted to address today is how to find essential subsurface minerals using this subsurface imaging technique, but at a low cost. So the traditional physics-based approach does require an accurate Earth starting model, like I've pointed out on the top left. And yeah, up here. So with a poor starting model, we don't end up with a great final result. But with a more accurate starting model, we end up with a much better subsurface imaging result. But on the right, if we use AI to use a purely data-driven approach with neural networks, we don't actually need an accurate starting model. What we need is a lot of examples of data to create a good generalizable model. And then the other challenge or problem I just wanted to address is that typically training we do on GPUs, and they can be expensive and hard to get a hold of. But in some cases for fine-tuning, we can actually use CPUs, and there's been some advancements with CPUs that make them viable for fine-tuning neural networks. So what I want to introduce is this OpenFWI. It's essentially a collection of synthetically generated data sets that are open source. So anybody can get on their website and try out the same things that I tried. And so they've released this kind of all these synthetic data sets. They have some great publications, tutorial code, and resources available on their site. Right now it's owned by University of North Carolina. But yeah, they've made this all open source, and so even the code for the AI-driven FWI is open source, so you're welcome to try it yourself. So just a little bit of background in the basics of wave field propagation. So on the top panel, I have some sample velocity models, and then we have wave propagation as the sound waves propagate through these models. We can generate corresponding seismic shot gathers. And so with this animation, we can see, at the top we have like a simulated sound source, and then we have the sound propagating through the layers and bouncing up, and then the bottom images are the corresponding seismic, like in time and in distance, the shot gathers that are generated. All right, so looking at the training, validation, and test data that I used for this experiment, it was one of those data sets from OpenFWI. And so the kind of the pairwise data set consists of one of those shot gathers and a velocity model image. And then we aim to get the model to predict one of these velocity model images directly from the shot gather. So I used a total of around 150,000 images of the seismic shot gathers, and then 30,000 of the subsurface models as the answer, as the ground truth. So it's a supervised training. And so I've just highlighted like a sampling of some of those training images here. All right, and the neural network that I used was called inversion net. If you've seen an image like this before, it's very similar to something called UNet. And I won't go into great detail now on this architecture, but if you want to learn more, you can go into the OpenFWI paper. And really, you can just Google OpenFWI to learn more. So I wanted to get into the results that I got just with this kind of this small experiment, simple experiment with a simple velocity model. They have much more complicated ones as well, but I wanted to demonstrate to myself that I could do this fine tuning on a CPU and that I could get a decent result. So on the top here, I have after one epoch or epoch, depending on how you like to say that, after the neural network's trained just a little bit, and you can see it. The prediction on the left is not super accurate, not super great, but after 50 epochs, we have a much better result on the prediction on the left compared to the ground truth on the right. And then on the right-hand side, I'm showing the training loss and validation curves over these 50 epochs. So, we do see convergence with these, and it's a good sign that we've, hopefully converged to a solution. All right, so I do work for Intel. I do want to show you that you can actually get started on the Intel Developer Cloud, which is new, and it is an exciting platform. It is very new since, I guess, November or so, put it out. But what it does is it would give you the opportunity to try out Intel's latest hardware and software, and we have a number of kind of notebook examples to be able to do that. So yeah, it's just a good opportunity. You can probably just, again, search for Intel Developer Cloud to get started. And yeah, I'll go to my conclusions here. So what I was able to do in this experiment was to successfully fine-tune a deep neural network without an accurate starting model to obtain a subsurface model. So that's the one challenge that I had. And then the other one that I had was training on a CPU. So in this case, I was training on a 4th gen Intel Xeon CPU. And one of the more recent advancements that has been exciting that I've tried is this advanced matrix extensions, AMX. And it accelerates some of the matrix multiplications that are required in any neural network deep learning. And I did highlight here just the little bit of code and like one line of code that basically I needed to do to run in a parallel fashion on the CPU. And so if you're using PyTorch, you can run in parallel using this torch backend Xeon run CPU command, and then specify this is how many machines I have, this is how many cores that I have that I want to use, and then run your training script. And so for me, it was eye-opening to see, okay, I've typically done this kind of thing on GPUs, like most of us have, but it was eye-opening to see, I could complete this in, I think it was 4 or 5 hours, the 50 epochs, and for this fine-tuning example, it was a great way that I could, do this in a cheaper way. So one thing I did want to highlight here at the bottom is that if you can fill out a survey here, be happy to get you some cloud credits to the Intel Developer Cloud. And also the other thing I don't have here on the slide, but my team is looking at hosting a Kaggle competition that's kind of based around this OpenFWI and expanding it to generative AI as well, where you could actually generate more images for your training set and supplement the data that way. So yeah, that's all I have. If anybody has any questions, happy to take your questions.